Today, the PCL Friday seminar is going to be given by Simon Wang. Simon is based in between computer science
And
science department with different supervisors in both.
yeah.
And the talk today is on understanding the quality of body movement by leveraging Wi-Fi sensing.
Yeah.
I look forward to the talk.
Okay. Okay. So first of all, thanks for inviting to give me this opportunity to give this talk. And before starting the presentation, I want to introduce myself. So I'm Simon, and I work with Nadia Bussos at UCL Interaction Center, which is the joint institute between the psychology department and the computer science department. And I also work with Kevin Chetty, specifically on the wireless sensing. So the topic I'm going to present today is understanding the quality of the body movement by leveraging the Wi-Fi sensing. So before I start the technical part, I give one example to ask what are the quality of the body movements. We know that let's say uh, detecting some physical activity, for example, the walking, standing, or sitting, waving hands. These are kind of the physical detection. But in terms of the quality, here I give an example. Let's say there's many people nowadays working in front of the computer for long hours. So basically, when they trying to sit or they trying to stand up, they may show some different variations for the simple and the same behavior, which is the sit to stand behavior. So let's say in this picture, even though the picture is very naive, but I show example that the user may experience a pain uh, impact on her back. So that when she trying to stand up, she's trying to behave some protective behavior, which try to avoid such pain. So one specific example is that the chronic pain limited the daily activities of sufferers. Those people with chronic pain often display some protective behaviors in their routine tasks. So, for example, a sit-to-stand behavior, individual may like using the armchair to support their standing. So, such quality represents for the behavior like the stiffness, hesitation, of showing the fear of the body movement. So that is something about the quality. So when you perform some activities, you show some quality of how you perform such behaviors rather than just detecting such physical behaviors. So we know that we have a lot of sensors can be used to capture body movements. So let's start from the optical sensors like the RGB camera. We also have the depth camera. And in terms of the wearable sensors, we have the IMU sensors. And for the sensor to detect physiological signals, we have the, for example, the EMG or PPG signal to detect the brain electronic activity and the heartbeat respectively. So so rather than using these kind of sensors, um, can we use different type of sensors because these sensors, as I mentioned, have some limitations. So I call them as the intrusive sensing. So basically, the camera require line of sight environments. So it's a limited coverage and it has the occlusion issue, or it simply raises the privacy concerns. And in terms of the wearable devices, they simply require the users to simply wearing them all the time. So may limit users for their physical movement, which avoid them to perform more naturally. So in contrast, the wireless sensors such as the Wi-Fi, millimeter wave, or other radio frequency-based sensors, they're considered as passive and ambient sensing. And in addition, they work under non-line of sight conditions. For example, through the wall, larger coverage, device-free with less privacy concerns. So we look at how does Wi-Fi sensing works. So Wi-Fi radios are transmitted between the Wi-Fi signal routers and receiver devices. So when, for example, a person is moving in between the signal propagation, as shown in this picture, this will the motion of the person will cause the radio waves to absorb, reflect, and diffract in different ways, for example. So this change of the signal propagation signature and such variations can be used to map different body movements. So current application including using the CSI, which is the channel state information, and extracted from Wi-Fi routers from the physical for physical activity recognition, such as the walking, sitting, or standing. Meanwhile, previous work put the antenna close to the chest to capture the chest movements. So then they can extract the Wi-Fi signal variations by the altered by the breathing, so indicating the respirations. Um, so previous work, I want to give a point that the previous study have focused on detecting different type of activities. Let's say we have mentioned walking, standing, and chest movement that related to physiological information. But however, there's still a little understanding how these signal can be used for assessing the quality of the body movement that reflected to different affective status. So for example, the quality of the body movement. So to answer this, we divide the research into three parts. So first is to construct the Wi-Fi sensing system to capture such fine-grained body movements. And secondly, we need to build data sets containing different body movements related to these pain protective behaviors. And thirdly, we need to develop algorithms that can identify different type of protective behaviors based on the Wi-Fi CSI datasets. So this figure illustrates the layout of our Wi-Fi sensor system in the room. And I need to mention this CSI was originally developed by Fang Zhan, who is the other PhD student from Kevin Chetty. So we simply reuse his device and do some modification for our study. So you see that the layout contains the four Wi-Fi devices placed at each corner of the room respectively. And the participants perform the activity in the central space. So this is the picture of the Wi-Fi router. And so to collect the data sets, we also put a camera to capture the ground truth videos as reference. So in total, we collected data from 16 participants, and each participant performed 5 activities, and each activity repeated for 3 to 5 repeats. Um, so it need to mention that the participants are healthy adult participants who are volunteered to involve in this study and who are performing those protect behaviors which we observed from the patient rather than we collect the data from patient directly. So here I list a diagram. So you see that we have 4 type of uh, different physical activities. Let's say sit to stand, stand to sit, bend and pick, and reach and grab. And for different physical activity, we define 3 different levels. So for example, sit to stand, we simulate 3 situations that we ask the participants to sit to stand normally, and then have 2 variations, which is sit to stand on the left side and the right side with different asymmetry level. So these 3 conditions simulates that the patient with back pain will sit to stand differently. And for each physical activity, we also divide it by 3 speed levels. So here we consider a fast, normal, and slow speed to reflect that the patient will perform rigidly or normally, or even the hesitation as with a lower speed. Here, I don't know. Okay, so here is an example. Um, So we simulate that people will do different activities, but containing different quality of the body movements. And you see that when people are doing different activities, the pattern from one link have significant variations. So here I give an example that we extract the amplitude and phase information from the raw CSI signals. So see that the different quality of the body movements actually brings different variations in terms of the pattern. So the x-axis is the time, and the y-axis is the dB, and on the right side is the phase information. So to build a machine learning algorithm to learn this activity for detecting different quality of body movement, so we simply starting from detecting the type of activity as the first step. So first, here we present a novel hybrid fusion stack LSTM architecture. So the use of LSTM is to encode the temporal relationship, which is well established in the area of machine learning. So it was an intuitive building block for our model. And the hybrid LSTM fused two LSTM neural networks, as you see from here. So the first LSTM on the left side capture the mid-level information about the type of activity to encode the signal. And we pre-train this model by feeding the amplitude and phase information extracted from the CSI. And with the ground truth label of 4 different type of physical activities of C2 stand, stand to seat, peek and forward, and grabbing. So after pre-train the first model, we constructed hybrid LSTM highlights on the right-hand side. So the second part of the LSTM is used to detect the protective behavior. We know that the fact is that the quality of the body movement is built on the top of detecting the type of the physical activities. So in this model, we add another LSTM in parallel with this pre-trained model, LSTM1. So, so this parallel feature extractor can extract the information while aiming to understand the interplay between the CSI information and then the ground truth protective behaviors. So in this structure, the LSTM1 layer is transferred from the pre-trained model and frozen during the fine-tuning at the second stage. And the multi-layer perception are added to for the latent feature extraction from these two LSTM subcomponents, then used to map the protective behaviors, as well as the lateral asymmetry and the movement speed level. So here you see some examples. We compare our algorithm with some benchmark using the shallow algorithms, let's say SVM, KNN, or simply multi-layer perception, which is constructed by several fully connected layers. So you see that each characteristic represent different persons. So see that the overall the accuracy for detecting the quality of the body movements across different participants are high as to 84%. Regarding the detecting of the protective behaviors, so let's say a lateral asymmetry, we have over 90% of the accuracy. And for the speed level, which have 3 classes, fast, normal, and slow based on the protective behavior, is as high as 92%. And here is the matrix showing different activity accuracy. So in general, our hybrid LSTM model shows an overall 92.3% across all classification tasks. So to conclude, our work is the first to use the Wi-Fi signal to assessing the quality of the body movements that related to pain behavior. And we construct a novel hybrid fusion stacked LSTM for assessments based on the Wi-Fi captured protected behavior signals, and evaluated the system on automatic detection of activity types, lateral asymmetry, and the movement speeds, including indicating the quality of the body movement. So in the future, we aim to deploy the system to assess people living with chronic pain in real-life settings. So we aim to migrate the system to patients' homes for real-world detection tasks. Yeah, that's all about to share today. Thank you.